Hello everyone, my name is Yuli Setio Indartono from Institut Teknologi Bandung. I and Mr. Aditya Muhammad Nur will present our paper with title Design and Testing of Thermosiphon Passive Cooling System to Increase Efficiency of Floating Photovoltaic Array in this 7th International Conference on Industrial, Mechanical, Electrical, and Chemical Engineering. As we knew, solar energy is virtually available everywhere. That's why solar energy plays a key role in energy transition. According to IRENA, solar photovoltaic occupies 25.3% of renewable capacity worldwide in 2020. This is quite big number of renewable energy. Floating photovoltaic is more efficient than on-ground photovoltaics. That's why the floating PV yield in a higher power output. Floating photovoltaics also eliminates the need for land use. According to National Electricity Company (PLN), fossil fuel-based power plant will be phased out start as of 2030. And then at 2060, there is no fossil fuel-based power plant. Variable renewable, solar and wind, will become the main foundation for national power generation in 2060. Nowadays, there are two very big floating PV projects, one at Cirata and the other at Batam. Those two projects show very progressive PV power generation development in Indonesia. To improve the performance of floating PV, I and my student, Bayu Sutanto, at 2017 developed Thermosiphon cooling system to reduce the temperature of floating PV. The water circulation in the Thermosiphon cooling system is driven by buoyancy effect at the bottom of the photovoltaic. The velocity of the natural circulation is around 8 millimeter per second. Photo on the left side show the laboratory scale of Thermosiphon cooling system applied for the photovoltaic system. A curve at the center show the efficiency of photovoltaic system on ground, floating, and floating with Thermosiphon cooling system. We can see that the efficiency of floating PV with Thermosiphon system is superior compared with ground PV and floating only. Curves at the right side show the power of ground PV, floating PV, and floating PV with Thermosiphon cooling system. We can see that floating PV with Thermosiphon cooling system show superior power compared to other systems.
Thank you, Dr. Yuli Setio Indartono, for delivering the introduction for this study and insight for the importance of renewable energy role in the future. This point forward will be presented by me. My name is Aditya Muhammad Nur. I am the co-author for this study. Now I will explain our data retrieval retrieval or experiment sim, here we divide our experiment into two categories, namely for PV array A and PV array B. PV array A will not be treated to any modification, whereas PV array B will be fitted with a thermosiphon passive cooling system. Both arrays were tested on the ground as well as above water or floating condition. Ground test performance result will serve as a baseline performance. We gave two designations for floating test. The normal floating test applies for PV array A and thermosiphon floating test for PV array B. After we obtain the floating test data, we compare the performance gain relative to the ground test performance data. Once the gain was identified, it can be compared to conclude the advantage of thermosiphon passive cooling. The experiment setup for ground and floating tests are presented in this slide. We utilize several tools such as MPPT, temperature data logger, solar power meter, PV analyzer, flow measurement to retrieve various data, namely PV power output, module temperature, solar irradiance, IV curve, and cooling fluid velocity. In this slide, we illustrate our measuring point to retrieve temperature data. Point A represents the measuring point on the PV module top surface, and point B represents the measuring point on the PV module bottom surface. Point C represents water temperature in the thermosiphon loop before passing the PV module, and point D represents water temperature after passing the PV module. We can observe that fluid temperature rises after passing the PV modules, which indicates that the heat is extracted away from the PV module into cooling fluid. Point E is the measurement point for water reservoir temperature. Let's put our attention towards the temperature profile of point C and point E. The water temperature is reduced to the value which is close to reservoir temperature, which shows that heat dissipation from cooling system to surrounding. Here we can observe the average temperature for each test condition at various solar irradiation. Ground test yields the highest module temperature range and highest average temperature. Both floating tests yield a lower temperature than the ground test. However, the lowest temperature range and lowest average temperature are achieved with thermosiphon floating test. Normal floating test temperature profile sits between ground and thermosiphon test. Now, since we proved that both floating tests yields in lower temperature, we assess the following for performance gain. Comparison is made between ground tests and floating tests along various irradiation values. PV array A experienced 7.49% gain in efficiency, which is improved from 9.16 to 9.81%, whereas average output is improved by 14.64 watts. We represent PV array B performance gain similar to PV array A by comparing recorded ground test result and floating result along various irradiation values. PV array B experienced 11.85% gain in efficiency, which is improved from 8.05% to 8.94%, whereas average power output is improved by 20.61 watt. After both arrays' performance gain have been identified, we can compare its magnitude between two PV arrays. Efficiency-wise, thermosiphon test achieved 3.53% advantage in efficiency gain, whereas power output advantage is 4.36%. This result demonstrates the performance advantage of applying a thermosiphon passive cooling system to a PV array. Finally, we arrive at the conclusion for this study, where we emphasize more on the advantage of the application thermosiphon passive cooling system. PV module temperature is lower by approximately 8 degrees Celsius, and then lower temperature yields in higher power output and efficiency with 3.53% and 4.46% gain respectively. Lastly, performance gain is a net gain since additional cooling system does not require additional power from the PV array. Thank you for your attention and have a pleasant day at 7 ICIMECE 2021 International Conference.